Okay, we have a problem here involving current. We have a high voltage power line that's carrying 50 amps of current, and we're going to determine the charge and the number of electrons that pass through a given point, i.e. under those little birdie's legs, in 1 minute. Well, we know that the current is equal to the charge per unit of time, so I equals Q over T, and we have been told that the current is 50 amps, and that the time is 1 minute. So we need to make sure that we substitute in for our time 60 seconds for our time. We need that time unit to be in seconds. So then from this we can solve for Q, and we get a Q value of 3,000 coulombs. So the next part of the problem then asks how many electrons pass through a given point there. Okay. Well, we know that we have 3,000 coulombs of charge, so if we have 3,000 coulombs of charge and each electron has a charge of 1.6 times 10 to the negative 19th coulombs, we can do a little dimensional analysis here and figure out how many total electrons we have. So our coulombs here will cancel out with each other, okay? And we will then be left with 1.875 times 10 to the 22nd electrons. Alright, here's a problem on Ohm's law. It says the heating element of a toaster carries 13.2 amps. It's quite a bit of amps going through there when it's connected to a 120 volt source like a normal electrical outlet. We're going to determine the resistance that that toaster carries. To do this, we're going to use Ohm's law, which we know is the voltage in a circuit is equal to the current times the resistance. So putting in the values that we know, we have voltage of 120 volts, a current of 13.2 amps, and we're solving for our resistance. So solving this out, we end up getting a resistance value of 9.09 ohms for the toaster. Makes you think twice about putting those Pop-Tarts in there, huh, kids? Alright, here's a problem on resistance and Ohm's law. So we have a tungsten filament of a light bulb that is 58 centimeters long. It has a cross-sectional area that's given and a resistivity that is given when the light bulb is first switched on. It says for us to determine the current in the bulb when it's connected to 120 volts. So in order to find that current, we're going to be using Ohm's law, which is the voltage is the current times the resistance. We know our voltage is 120 volts, but we do not know the current, which we're trying to find, and we also do not know the resistance. Now we are given enough information to find the resistance by using our resistance equation. Okay, that equation is given by the resistance is equal to rho, which is kind of a script letter P, which stands for the resistivity of the wire, times the length of the wire, L, divided by the cross-sectional area of the wire. So plugging our values in, we will first plug in that resistivity value, which is 5.6 times 10 to the negative 8, and that's ohms per meter. That's our value for rho. Then our value for the length of the filament, which is 58 centimeters long. We need to end that in meters, so that's why we'll write 0.58 meters. And then we'll divide that by 1.6 times 10 to the negative 9th meters squared. So calculating that out, we will get a resistivity value here of 20.3 ohms. Now it's important for us to have that resistivity value or the resistance value of 20.3 ohms, because now I can take that resistance and go back to my original equation. Remember, the problem is asking me to find the current that is in the circuit. So now that I have 120 volts, I have my resistance of 20.3. I can simply now solve for my current, and when I do that, I get a current value of 5.9 amps.
Hey everyone, here's your Sioux Falls physics teachers, and today we're looking at a question involving electrical power. In this situation, we have the heating element in an electric stove. Several pieces of information are given to us about this wire, and we are to determine the power used when the stove is connected to 240 volts. Well, the first thing that we need to do is actually look at the resistance of the wire that's being used. And remember that our formula for resistance includes the resistivity times the length divided by the cross-sectional area of the wire. All of those pieces of information have been given to us in the problem. Resistivity is 8.2 times 10 to the negative fifth. The length is 1.2 meters. And the cross-sectional area is 3.1 times 10 to the negative 6 square meters. Putting those together, we find that the resistance of the wire in the heating element is 31.74 ohms. Now, the next piece of information, if we want to include the power, would be to look at our equation that is power equals current times volts. Now notice that we do not yet have the current value used by the wire. We could certainly find this and calculate a value in amps. We could also easily replace the current with the equation volts divided by resistance. So if we replace that then, kind of an easy little derivation, we have voltage squared divided by resistance, and that kind of gives us a shortcut to determine the power. So in this case, our power, the voltage was 240 volts, resistance was figured at 31.74 ohms, and calculating that out, we find a power of 1815 watts. Notice that we would have found exactly the same answer if we had included an actual value for the current and included that in the equation multiplying by the voltage of 240 volts. Hey everyone, here's your Sioux Falls physics teachers looking a little bit more at electrical power. This problem gives us the wattage used by a hairdryer when connected to 120 volts, and we are to determine the resistance and the total energy used in both joules and kilowatt hours for 6 minutes of use. The first thing that we're going to do with this is to look at the resistance. And we can do that by going back to our equation for power. Again, power is equal to current times volts. We have the power amount, we have the voltage amount, but what we're actually looking for is resistance. And again, remembering from the previous problem, we can take this current value here and replace voltage over resistance. And if we do a little bit of algebra, we simplify that out to get voltage squared over resistance. So with the information given to us in the problem is 1,250 watts for the power. The volts is 120 volts. And our resistance is unknown. Solving for R, we get 11.52 ohms as the resistance of the hairdryer. The second part of this question asks about the total energy used. And for that, we need to go back to our definition of power. Originally, we defined it as a rate of work per time or energy over time. And in this case, then, we are given the power amount as 1,250 watts. Remember that really a watt is the same as a joule per second. So if we are looking for the amount of energy that is used, we simply need to plug in the amount of time, putting that in seconds, and we can plug in then 360 seconds and solve for energy, and we get a value of 4.5 times 10 to the 5th joules. So that would be the energy used in joules over 6 minutes by the hairdryer. Now the second portion of this is to calculate the energy in kilowatt hours, because of course that is how we are normally billed for electricity. Notice that a joule, as we found earlier, is a label for energy. Kilowatt hours is also a label for energy. So we could ideally just take this value of 4.5 times 10 to the 5th and use a little conversion factor to get to kilowatt hours. But we can also easily get this, and probably a little bit easier to see how we're doing it, if we go back to our original equation of power equals energy over time and substitute slightly different labels this time. Originally, we had 1,250 watts. If we convert that to kilowatts by moving the decimal, we would have 1.25 kilowatts. We are again looking for energy as our unknown. And this time, as we plug in the time, rather than putting that 6 minutes into seconds, we're going to put that 6 minutes into hours instead. So if we take 6 minutes, convert that into hours, we see that, of course, that is 1/10 of an hour. And now, if we solve for energy, this time the label that we get would be equivalent to having our kilowatts here, multiplied times our hours here, and we get 0.125 kilowatt hours as our label. Hello again, Sioux Falls physics teachers looking more at electrical power. This time we're combining it with other types of energy, specifically thermal energy. We have an immersion heater with a given resistance connected to 120 volts and is used to warm 250 grams of water. Assuming that all of that energy goes into the water, determine the change in temperature after 4 minutes. Well, our first step here is going to be to figure out the power supplied by the immersion heater. And similar to previous examples, our equation for power is current times volts. That can be rewritten as voltage squared over the resistance, which uses the information straight from the problem that we're given. In this case, that's 120 volts. The resistance value is 115 ohms, and so the power of the immersion heater then is 125 watts. Now notice that that power is being supplied for a time period of 4 minutes. So our next step will be to figure out then how much energy we have as a result of that. We can go back to our definition for power, work over time or energy over time. So if we have 125 watts and that is applied for 4 minutes, putting those minutes into seconds, we get 240 seconds. That gives us a total energy then that can be given to the water of just over 30,000 joules. So 30,052 joules of energy will go into the water. At this point then, we can go back to an equation from previous units on thermal energy. When we talk about thermal energy, remember that our label is Q, and that is equivalent to the mass times the specific heat times the change in temperature. So in this case then, we can take the energy amount that we just received, put that in for Q. Notice that our label for specific heat given in the problem is 4,186 joules per kilogram. So that means that this mass of 250 grams of water will need to be changed to kilograms. That specific heat, again, 4,186. And finally, our change in temperature, which is our unknown. Solving for delta T, we then get a value of 28.7 degrees Celsius as the resulting change in temperature from that energy. If you click down this link, you must want to know more about how electrical power can be used together with motion. In our example here, a 12-volt electric winch is used to lift a 925 kilogram load at a constant velocity of 0.05. Determine the current and resistance of the circuit. First of all, we want to figure out the power that's going to be required for this load to be lifted. And remember, we've talked a number of different ways to calculate power, but one of these shortcut equations that is on your equation sheet that can be used, especially when we look at motion, is the equation force times velocity. In this case, we are given the mass of the load at 925 kilograms. And then if we multiply that times 9.8, we will get the force required, and the velocity that is given to us is 0.05. Multiplying that out, we find that the power required in this situation then is 453 watts. Next, we'll use this information to find the current and resistance. And notice that since we do want both of them, there probably isn't much point in us using the shortcut equations of combining power and voltage. So instead, we'll simply go to our equation power equals I times V. Power has just been calculated at 453 watts. Current is our unknown, and the voltage is given in the problem as 12 volts. Solving for I, we find 37.8 amps of current are required in that circuit. Finally, now that we have the current, we can go back to our Ohm's law equation of V equals IR. 12 volts is given. We've just solved the current to be 37.8 amps, and that leaves us with an unknown resistance, which turns out to be 0.32 ohms as the resistance for that load lifted at that given velocity.